it's so many Tesla meter squares or so many Webers. So this fact is good to know to simplify coming up with an answer to a question that would otherwise be a difficult question to answer. If you know that result, then you can just, sort of like change the question around, do an easier problem, and then adjust that answer, right, to the original, more difficult question that was asked. Anyway, and then there is the RL circuit. We did the RC circuit. Did we do the RC circuit?
Yes.
Oh yeah, we did. We even did a lab on it, right? So what would happen if you have a resistor connected in series with an inductor of length L? I mean, not length L, of inductance L. So this is the RL series circuit. Okay, so what is RL connected in series, to a DC battery? The condition is that we have, let's say, a battery like this. And we have, the circuit symbol for the inductor is a coil. So when you see a coil, that's an inductor. The resistor is like this. That's not a coil, that's a resistor. And we can call this, plus, minus, we can call it E or delta V. I'll just call it E, like we did for the case of the capacitor, right? And we have a switch. What if we have a switch? And we close the switch at t is equal to 0. So at the instant that you close it, that's t is equal to 0, the current is 0. Right? I mean, initially there's no current. I mean, it was open. There was no current, and then I closed it, so it started with 0, right? And then what will happen is that there's going to be a current in the circuit. In which direction do you think the current is going to be? Clockwise or counterclockwise in this circuit? Which one?
Clockwise.
Clockwise, yeah. So the current is going to be this way. And it's going to be this way. So I'm going to label the current with a lowercase I because it'll be changing with time. So let me erase this board. So if I do loop rule, you thought you were done with that, right? The sum of the voltages around the loop, right, is equal to 0. So how about I go clockwise, and I am going to start over here. How about I start over here? Okay, as I go up, what should I write down as I go through this battery? This is a DC battery. The voltage is always the same. So what should I write down? Just the EMF E, right? And then when I go through the inductor, remember that we wrote that the EMF was what? Like minus L di dt. Right? So what I do is the following. What should I write down when I go through the resistor? Plus or minus. If I'm going in the same direction as the current.
Minus.
Minus IR. So I write it as minus for the inductor. Minus, and then the voltage across the inductor is L di dt. That's the formula that we learned in this chapter. So minus L di dt, and then I complete the loop, and that equals 0. So notice the following. If I solve for E, right, I get L di dt plus IR, correct? If I solve for B?
Is that a differential equation?
Is that?
I said, is that a differential equation? Is that what we're going with?
Yes, it is. But it's first order, and we have a lot of constants in there, so I can just separate it. And I don't have to use the formal techniques to solve it. So we can still solve it, like we did for the case of the RC circuit.
I have a question. Why is it not a positive L di dt?
So when I go, see, this is the higher potential,
Yeah.
and this is the lower potential. So as I go from here around my trip like this, I'll be dropping in potential. So the potential here is higher than the potential there. Potential here is higher than the potential there. So
Yeah, I thought-
drop, 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 and then I get over
So
here.
if you go in the same direction as the current, it's negative,
Right.
but then
But then one has to be
It's
careful
also
also with,
negative.
but one also has to be careful with the sign of that. But right now it's going, the current starts at 0 and it's going to be increasing. So I'll just say it's negative if I go in the same direction as the current.
okay, I'm just confused to why the two negatives don't cancel out.
So this is the potential difference. This is a voltage, right? That's a voltage, that's this voltage over here, which is E. Right? So the minus sign has to do with opposition to the change in the current. But the voltage in this circuit from here to here, the voltage drops. So it'll be minus, and then I'll just use the magnitude of that voltage in the inductor, L di dt.
Okay.
I'll just use like, it's like over here, right? I mean, remember what the meaning of this minus sign is, right? That's just to oppose the change in the flux. The magnitude of that voltage is going to be 3 volts, 5 volts, 7 volts. That's the difference between these 2 points. But as I go in this direction in this circuit, I'm dropping in potential, right? Until I get here, and then I go back up.
Okay.
So that's why I said there are 2 things to consider. If the current is increasing and you go in the same direction as the current, write it as a minus, L di dt. Okay? Now, at t is equal to 0, what did we have? The current was 0, right? Thus, I'm just gonna, consider that equation at t is equal to 0. Then I have E equals L di dt. Notice that the rate at which the current increases depends on L. In other words, the higher the inductance, which we said it's a measure of the opposition to change in current, the higher the inductance, the more slowly the current is going to increase to the final value, whatever that final value is going to be. Right? So the higher the inductance, the greater the opposition to changes in current. So the higher the inductance, the more slowly the current is going to change, because it's opposing that change. So the current is going to be increasing more slowly. It'll take longer to reach the final current, right? Eventually, this circuit, we can say that, after a long time, the current will be like the final current, capital I. But it started out at 0, and after a long time, after some time, it's going to have its final value of capital I. And so the current is going to be increasing Right? So what I expect when I solve for the current, what I expect is this: if I do a graph of current as a function of time, right? Initially the current is 0, and later on, right? It's not gonna get bigger than that. That's what I expect. But if I this is the equation, right? That tells me what the current is and how the current is changing at the specific instance of time, how it relates to the voltage of the battery. Maybe I shouldn't use E, because you might think that E, I should call it EL for that one, and this is different. This is for the battery. So this is EL. Maybe I should be more explicit like that. And this is E for the battery. This is E for the battery. Now, how do we solve this guy over here? So that's just something to note. Just note that the bigger the inductance in the circuit, the more slowly the current is going to be changing. Right? That's what that is. Okay, that's one way to look at it, right? Or another way to say it is that if the inductance is smaller, just to make a relationship with the curve over there, if the inductance is smaller, then the current is going to grow more rapidly. Right? And this, by the way, is the slope, the IDT on that curve over there. If I take the IDT, if I take the current, if I take the IDT, that's the slope of the tangent line, right? To the curve. So notice that at the beginning, the tangent line to the curve, it's something like this. And that's like a high slope compared to this, compared to that. And over here, the slope is 0. That's when the IDT will be 0. So said differently in an opposite way, the smaller the inductance in the circuit, the bigger this current is going to be, the bigger this dIdt is going to be, so the bigger the slope, right? Which means the more rapidly it's going to change. Right? So that's another way of looking at it. But if I look at this equation over here, I have, what if I divide by, let me write L, the IDT like this, and then E minus IR. And what if I divide by L? Like that, right? Yeah, it'd be nice to have this, be nice to have that I by itself. So, let me factor out R instead. So this would be R. So this would be E over R minus I, right? And this is L dIdt. So L over R dIdt will be E over R minus I. I guess I'm just going in circles over here. The I will be E over R minus I equals R over L dt, which I guess I could have done right away from here. Anyway, right? I could have just moved this to here too, and then this to that. It's essentially the same thing. And then I want to integrate this. I have an dI, and I have an E over R minus I equals R over L dt, and I integrate that. R and L are constants. And I integrate from t is equal to 0. That's the instant when the switch is closed. At that instant, the current in the inductor is 0. And I'm just going to consider a later time t. And this will be a later current I. So how do I do that integral? Okay, so let me make a substitution. U equals the thing in the denominator, which will be E over R minus I. So du di will be minus 1. So du is minus di. So therefore di is minus du. I'm going to take this and I'm gonna put it in here in the numerator. So the integral becomes the integral of the I in the numerator, which is minus du, and then this whole thing is u. And then I have minus r over L dt from 0 to t. Notice that I can bring this minus sign to here, so that I have the natural log of u equals minus r over L, and this is just going to be t, correct? So this will be the natural log of u, but u was this. So this would be e over r minus I, evaluated from I equals 0 to I, equals minus r over L t. I'm supposed to get to something like this. And then I evaluate this will be the natural log of e over r minus I, minus the natural log of e over r, which is minus r over L t. And then I gotta do the natural log of this divided by that. And then this is to the exponent base e. So that means that e over r minus I over e over r equals e to the minus r over lt. And I can cross multiply. So this is e over r minus I equals e over r e to the minus r over lt. So therefore I equals, I just bring this over here and this over there, and I'll just save a step. I'll just factor it. And this will be the current as a function of time. Now let me check. Did I do that right? I kind of rushed over here. I know we have to end. Kind of did that quickly over there. But let me just check. I'll just erase a couple of lines over here. Check. At t is equal to 0, what do I get? Initially, right? At t is equal to 0, what am I supposed to get? The current is supposed to be?
0.
0. So, if t is equal to 0, how much is e to the 0? 1. And 1 minus 1? 0. I'm good. And how about after a very long time, like at infinity? You know, a long time. I wait long enough for the current to establish. So how much is e to the minus infinity?
0.
0. 1 minus 0 is 1. So the current is e over r. And because this is constant, di dt is 0. That's why we're over here, because the current is now constant. And if di dt is 0, if the current is not changing in the circuit anymore because it reached its final value, what will be the voltage across this? What will be the voltage across this inductor? The voltage across the inductor depends on how quickly the current is changing through the inductor. So the voltage, you know, the EMF across this inductor is going to be 0 because if the current is not changing, the flux through it is not going to be changing. So there's no voltage. So all of this voltage appears across the resistor. So that's why I get E over R. It's the voltage in the battery divided by the resistance. And this voltage plus this voltage has to be this voltage over here. So for example, in the case of the lab that we did, suppose this EMF of the battery is 3 volts. And that's always 3 volts. Initially, at t is equal to 0, there is no current. So the voltage across the resistor is 0. So what must be the voltage? What must be the voltage across the inductor, which is, you know, the E sub L? It has to be 3 volts. And as time goes on, the current begins to get bigger. And as the current gets bigger, the voltage across the resistor gets bigger. So then this will grow to 1 volt. When that one is equal to 1 volt, the voltage in the inductor is going to be only 2 volts because the sum of them, 1 plus 2 has to be 3 because they're in series. And well, the voltage across the inductor is less because the current is now changing more slowly. Yes, and as time goes on and the current gets bigger, when the voltage through the resistor becomes, a bigger current, you'll have a bigger voltage, let's say 2 volts, then here, the current in the inductor has to be 1 volt. And when the voltage across the resistor reaches 3 volts, well, at that point, the voltage across the inductor has to be 0. And that's when you have a final current, and that's when the IDT is equal to 0 in the inductor. So there is a voltage in the inductor only when the current through the inductor is changing. If it isn't changing, if it's constant, the voltage in the inductor is 0. Because remember, if the current is constant, the magnetic flux is constant, and so there's no back EMF. There's no induced voltage in the inductor. It only exists for as long as the current is changing in the inductor. Anyway, this is like a plug and chug type of question. You might have some questions where you have to use this. How long does it take it for the current to increase to 50% of its final value? And you just plug the numbers in, and it's not so bad. Okay, I'll see